Hi, my name is Scherrer and I'm here to present a work on the LOFT algorithm, which is an efficient and scalable algorithm for detecting overuse flows. This work is the result of a collaboration between three research teams. These research teams include Professor Hsu-Chun Hsiao's team from National Taiwan University, Professor Nele Mentens' team from KU Leuven, and a team from ETH Zurich, where I pursue my PhD studies under the supervision of Professor Adrian Perrig. To start, I will quickly motivate the problem that the LOFT algorithm tries to solve, and I will explain what this problem has to do with mice, elephants, and rats. In summary, the LOFT algorithm seeks to distinguish flows by their size. When I say flow, I mean network flows in the sense of packet sequences that can be associated with a single connection between two network participants. There are many use cases that rely on distinguishing flows by their size. For example, the defense against distributed denial of service attacks or DDoS attacks, where large flows must be blocked, or load balancing, where flows of varying size have to be assigned to different services such that each service experiences the same traffic volume. As the flow distinction problem is thus an important problem, it has been extensively studied and has been addressed by many proposals. These proposals generally assume that resource constraints do not allow stateful monitoring of each individual flow, and therefore suggest probabilistic schemes with reduced accuracy but also reduced memory consumption. Moreover, probabilistic traffic monitoring algorithms generally try to solve the heavy hitter problem, where a few very large flows have to be distinguished from many small flows. In the literature, the small flows are often termed mouse flows, whereas the large flows are termed elephant flows, in order to emphasize the order of magnitude difference in flow size between these two flow categories. The goal of heavy hitter detectors is then to distinguish mice flows from elephant flows. However, we observe that only detecting elephant flows is actually insufficient for many use cases. To see why, let's consider the example of DDoS defense based on flow volume allowances. We consider a scenario where the full bandwidth is allocated to a given number of flows, where each flow has a volume allowance that corresponds to the typical volume of a mouse flow. Clearly, if any flow in this scenario overuses its allowance, other flows will experience congestion and loss, so allowances must be policed. If now an elephant flow detector is used to police these allowances, elephant flows which grossly overuse their allowance will be swiftly and reliably detected. However, elephant flows are not the only flows that cause damage. Instead, rat flows, meaning low-rate overuse flows that are only a bit larger than legitimate flows, actually cause damage as well. If a heavy hitter detector is used, such rat flows are not detected as overusing, although they still cause damage, especially if they occur frequently. Hence, our work tries to solve the problem of detecting all overuse flows, meaning not only elephant flows, but rat flows as well. To solve this problem, we start from the observation that the overuse detection performance of a monitoring algorithm depends on its measurement error. Only flows with a size comfortably exceeding the measurement error can be reliably detected. To detect low-rate overuse flows, this measurement error must thus be eliminated. However, the problem with existing schemes is that their measurement error can only be eliminated with large amounts of memory. These large amounts of memory are generally not available on high-speed routers where the flow monitoring must be performed. On these routers, all data relating to flow monitoring must fit in fast caches to not impede packet forwarding. So, to reduce the measurement error by other means than simply increasing memory, we have to understand where the measurement error comes from. To illustrate the source of this measurement error, let's consider the count-min sketch, which is a classic example of a probabilistic flow monitoring algorithm. The count-min sketch operates with multiple counter arrays. When a packet comes in, the flow ID of the packet is mapped to a counter in each counter array, and these selected counters are then increased by the packet size. This multi-mapping is performed for all packets in the stream, so flows regularly share counters. At the end, the count-min sketch then estimates the size of a flow by taking the minimum value of all counters associated with a flow. This estimation is affected by two types of noise, which we call counter noise. First, one source of noise are the uneven flow sizes within a single counter, which may lead to small flows being mistaken as overuse flows if they are in a counter together with an overuse flow. Another source of noise are the uneven numbers of flows across counters, which may lead to small flows being mistaken as overuse flows if they share a counter with many other flows. This counter noise is already partially addressed by using multiple counter arrays. However, the counter noise of the second type can be addressed even better by taking into account the cardinality of each counter, meaning the number of flows mapped to each counter instead of only the flow volume added to the counter. Our LOFT algorithm leverages this noise reduction idea as follows. Similar to a count-min sketch, LOFT maps flows to counter arrays. However, each flow is mapped to only one counter array, where the used counter array is exchanged in regular intervals, which we call minor cycles. At the end of a major cycle, which contains multiple minor cycles, LOFT asynchronously analyzes the counter arrays collected over the major cycle. In this analysis, LOFT first reconstructs the counter cardinality from a sampling-based active flow list. In other words, LOFT knows which flows were active during the major cycle and computes how many flows were mapped to each counter. Then LOFT estimates the size of each flow based on two sums. First, LOFT computes the volume sum as the sum of the values of all counters associated with the flow. Second, LOFT computes the cardinality sum as the sum of cardinalities of all the counters associated with a flow. The flow size estimate is then the ratio of these two sums. Flows with a high flow size estimate are then monitored individually afterwards. It is important to emphasize that while this estimation might be computationally intensive, it can be performed asynchronously and does not impede packet forwarding at all. After explaining the LOFT algorithm, we now turn to evaluating its performance. For this evaluation, we focus on two important requirements, namely estimation accuracy and processing efficiency, where we first discuss estimation accuracy and later discuss processing efficiency. To evaluate the estimation accuracy of LOFT, we rely on detection delay as an evaluation metric. This detection delay measures how long a monitoring algorithm takes to detect a single overuse flow within many non-overuse flows. The figure on this side illustrates the detection delay for different detectors to overuse flows of varying size. This overuse flow size is represented by the overuse ratio on the x-axis. Most importantly, the figure clearly illustrates that only LOFT can detect flows with an overuse ratio below 3, so the stereotypical red flows that we set out to detect. All other detectors cannot detect these overuse flows within the experiment duration of 300 seconds. Admittedly, LOFT takes longer than other detectors to detect very large flows. The reason for this higher delay is that LOFT must always perform at least one whole major cycles to get flow size estimates. Still, since the major cycles took 250 milliseconds in this experiment, we see that LOFT generally requires only one major cycles. Therefore, LOFT can also detect elephant flows within a reasonable time frame. These results are confirmed by similar experiments with traces with more flows and experiments building on K-dot traces. Moreover, we provide proofs about the accuracy bounds of LOFT in the technical parts of our paper. It is interesting to analyze where the accuracy improvements by LOFT come from. In the design of the algorithm, we hypothesized that varying counter cardinalities are a strong source of noise in previous schemes, and that more explicitly accounting for counter cardinality would thus reduce estimation errors. To test this hypothesis, we evaluate LOFT with and without considering counter cardinality. The results of this comparison are shown here as a cumulative distribution function of the detection delays obtained from 100 experiments, each for cardinality aware LOFT and cardinality agnostic LOFT, These results clearly show that detection delay can be strongly reduced by additionally taking counter-cardinality into account. Finally, we now turn our attention to a potential Achilles heel for LOFT, which is given by its reliance on an active flow list. LOFT needs an active flow list to reconstruct the counter-cardinality values, which are crucial for its accuracy. This active flow list must be obtained from sampling, which might be computationally expensive when done comprehensively. On the other hand, infrequent sampling might distort the counter-cardinality values and thereby the flow size estimates. To investigate the impact of infrequent sampling, we compare the detection delay of LOFT for varying sampling miss rates. The results show that while comprehensive sampling is important, LOFT can detect low-rate overuse flows even with infrequent sampling and is thus still superior to other schemes in this regard. These other schemes cannot detect these low-rate overuse flows within 300 seconds. Clearly, LOFT thus fulfills the requirement of accurate estimates. But what about its processing efficiency? We consider processing efficiency to be composed of two aspects, namely memory overhead and operational overhead. We will first discuss the memory overhead and its implications for processing efficiency. First, it is important to understand why memory overhead is important at all for processing efficiency. To see the reason, let us first look at the different access times for different kinds of memory. Experiments show that while a main memory access takes at least 50 nanoseconds, a cache access takes 1 to 20 nanoseconds depending on the cache type. If we compare these access times to the time allowance of 100 nanoseconds per packet on high-speed routers, it becomes clear that high-speed packet processing is only possible with algorithms which fit all their data into the cache. To show that LOFT is much cheaper in memory terms than equally accurate algorithms, we compare the memory consumption of LOFT, which is around 300 kilobytes for 400,000 flows, to the memory overhead needed for the individual monitoring of all flows, which is around 3 megabytes. This comparison shows that LOFT reduces the memory requirement by more than one order of magnitude compared to individual monitoring of all flows. In fact, the memory requirements of LOFT are so low that all relevant data structures easily fit into fast cache, which enables fast processing. In addition to the memory overhead, we also consider the overhead introduced by additional non-memory related operations for each packet. From a theoretical analysis of the algorithm, we already see that LOFT introduces a quite modest overhead of this kind. In particular, LOFT only requires one hash and one addition per packet, whereas other schemes usually require multiple hashes and arithmetic operations. We test this hypothesis of modest overhead with two different implementations, one in the Intel DPDK framework and the other for Xilinx FPGA. First, a performance evaluation of the DPDK implementation shows that 16 cores can achieve line rate for a realistic internet traffic mix. More importantly, however, is how LOFT compares to other probabilistic monitoring algorithms. Our LOFT DPDK implementation achieves a maximum packet rate of around 6 million packets per second per core. Hashpipe and HeavyKeeper, which were the two schemes which were the least inaccurate compared to LOFT, but still considerably less accurate, do not even achieve half that packet rate. Moreover, the packet rate of the DPDK implementation is far below that of our FPGA implementation. In particular, the Xilinx FPGA used in our evaluation has two NICs, each operating at a frequency of 200 MHz. Each NIC is running a separate LOFT implementation. Since the LOFT implementation on each NIC can process a packet in a single cycle, the FPGA can process 200 million packets per second per NIC, or 400 million packets per second in total. For an internet traffic mix, this packet rate means that the LOFT monitoring could keep up with the stream of packet level information from a link that carries over 700 gigabits per second. To be clear, the FPGA itself would not forward the packets in this setting, but would only asynchronously check the packet header information. Hence, LOFT is suitable for high-speed packet processing. In summary, our goal was to be able to detect all overuse flows, so not only extremely large elephant flows, but also rat flows, which are only slightly larger than legitimate flows. To detect these flows, we had to eliminate the measurement error of probabilistic monitoring algorithms. This measurement error stems from counter noise, which can be qualified as composed of two types. Our central idea is to reduce this noise by additionally building on counter cardinality instead of only computing volume-based flow size estimates. The resulting LOFT algorithm is unique in its ability to find low-rate overuse flows with an overuse ratio below 3. Moreover, LOFT is suitable for high-speed packet processing, which we confirm with a DPTK implementation and an FPGA implementation. With that, I conclude my presentation and I'm looking forward to the Q&A. Thanks for the attention.